So we are talking about we have seen in the conduction cases, heat conduction, we got the idea of the heat flux. So heat flux, you have seen this heat flux, if you write it down, that's heat flux is termed as the Q. If it is along is the vector quantity. If it is along x direction, Qx, along y direction, Uy plus long. This heat flux is due to the temperature should be a function of x. So there is a temperature variation due to the x. This should be temperature should be a function of y because there must be a temperature variation along y axis. This is there must be a temperature variation along z axis. So summing up all, temperature is a function of x, y, and z. These are three-dimensional case. 3D case. In case of 2D, temperature is a function of x and y only. That is a 2D case. And temperature is function only on x. That is the one-dimensional case. When we come from 3-dimensional to 2-dimensional, 2-dimensional to 1-dimensional, that is depends on the things. Let you take here. Here, what is the temperature gradient? Del T del X. Here is the temperature gradient. Del T del Y. Here is the temperature gradient. Del T del Z. If del T del X is much greater than other two's gradient. If it is much greater than, let you take it is some 100 degrees centigrade per meter. These two are the 5 degrees centigrade per meter and 3 degrees centigrade. Very less than 100 in comparative to 100. So we can neglect this thing. We're considering temperature is only varying along x. So 3-dimensional problem we can reduce to 1-dimensional problem. 3-dimensional problem can be reduced to 1-dimensional problem. Whatever the consideration is there, it is with the spatial coordinate. It's with the spatial coordinate. Along with the spatial coordinate, if time you include space plus time, then it becomes unsteady state. So temperature, if along is a function, temperature is a function, along with x, y, z, if it is also the function of time, then the problem will become unsteady conductive heat transfer. 3-dimensional unsteady conductive heat transfer. If the temperature, so time invariance. Steady state means time invariance. It does not vary with time invariance. In the steady state, it does not vary with the time. In short, we are writing it down. The steady state time invariance. That means it does not depend on time. So temperature is not a function of time. It may be function of space. It may be function of along x, y, z, but it's not a function of time. Unsteady state is a time dependent. So temperature is a function of time also. Time also. So that means temperature is a function of X, Y, Z, and T. So temperature having a how many gradients? Del T is varying with X, del T varying with del Y, del T varying with del Z, and del T varying with. It's the unsteady problem. This problem is the unsteady problem. Steady problem, unsteady problem. Two kinds of the conductive heat transfer we are considering. Most easy is the one-dimensional cases. So one-dimensional cases is the only this we are considering. Now one-dimensional steady. This cut and this is also steady. One-dimensional steady state. If you consider, that means del T del X, which we can write dt dx, partial differentiation in form of ordinary differentiation, because T is only function of X. It is not a function of Y, Z, and T. Small t, time. So this we are considering previously in the whenever we are talking about first time the Fourier's law. And what was that? In the case of the plane wall we are considering, in that case we are writing it down, the things, that is, if you remember, Ux equal to minus K dx. This equation was written for the one-dimensional. This is always valid. This is always valid. But this ordinary differentiation comes because of it. Steady state. This is always valid. But steady state should be mentioned here. Otherwise, if it is not steady state, it will come in this. This is always valid. This equation we can write anytime, any moment. This is a constitutive law. But dt, where dt dx we are writing or del t del x we are writing. That you have to consider this thing, steady or unsteady. This is for the one-dimensional unsteady state. Unsteady state. This differentiation you have to do it. Now, very one small example we are telling, the plane wall concept we are taking it, and we'll discuss about it here. One dimension, steady conductive heat transfer. That is the most easier thing. One dimension, steady conductive heat transfer. Before telling this thing, one thing I should have told previously, you have understood that the K is the thermal conductivity. This thermal conductivity also may vary with X, Y, Z, and time. Temperature, sorry. Temperature. It also may vary with this. It may vary with X, Y, Z, and T. Is the temperatures. It is not time. Temperature. Don't be confused. Capital T, we are writing for the temperature, and this is the spatial coordinate, X, Y, Z. Thermal conductivity also vary with the X, Y, Z, and T. So in that case, two assumptions we have to take. One is the isotropic material. Whatever the material you are selecting is isotropic material. That means direction independent. Spatial coordinate independence is there. So that means K is not a function of X, Y, and Z. is not a function of x, y, z. If you're considering, and you consider the variation of K with respect to temperature is also negligible. If you consider the variation of K with respect to temperature is also negligible, that means here the K is also very not depends on the temperature. So almost we can say here that K is a constant. So whenever we are telling about this thing, the thermal conductivity is a constant. In that time, we have to mention isotropic material, and as well as the variation of the K with respect to the temperature is also negligible. If you are not mentioning these two assumptions, it is incomplete. Because K might vary. Definitely K will vary with temperature. Thermal conductivity is a property, it might be a thermophysical property, it may vary with the temperature. It always varies with the temperature. But this variation is negligible. You have to mention that would be our assumption for the case of the one-dimensional steady conductive heat transfer. Now we are going to discuss it very slightly. We are telling it later. We also discuss with the boundary condition, but it is a very preliminary idea I am going to give you. What is happening? This plane wall concept we are taking again, one-dimensional concept. One plane wall we are considering here. One plane wall we are considering here. Plane wall. One-dimensional steady condition. So T is a only function of X. Is not a function of Y, and T is not a function of Z. Hence, it may be linear, it may be non-linear. It may be linear, it may be non-linear. How it is depends. Whether T is linear or non-linear. That we'll see later. This is the implication I'm giving to you. This T is a function of X, but it may be a linear function, it may be a non-linear function. Now our consideration is the plane one. In case of the plane one, so here, if you take this thing, X and Y direction also, we're talking about it, the very large. So variation of T, temperature with respect to Y and Z are negligible here. Negligible. As this, because temperature variation along Y-axis and Z-axis is negligible. Why? Because the Y and Z is very large. As the Y and Z is very large, so this is very higher. Variation is very less. So in that case, the variation is very less. So in that case, the variation is very less. We are not considering this thing. Okay. So one-dimensional problem, how to tackle this problem? How to attack this problem? This kind of the problem when we are telling. So in that case, this is your dimensional you are taking, that you take in this side X direction. Y direction we are not taking, we plot only temperature. Here we are plotting temperature is there. No variation. So here is the temperature that you take is the T1. Here your temperature is the less temperature T2. So hence you can see the plotting, according to the plotting, T1 is greater than T2. as T1 is greater than the T2. So heat flow will be happen. Heat transfer will be happen in this side that you are taking as the heat transfer. Okay. Heat transfer is the Q. Now, you take one at here, the same type of okay. So at X, distance it is, let you take X. At X, there is a heat flux, QX. At X, heat flux is QX. QX. What is that? That is nothing but minus K dTdx. Minus K dTdx. What is the Q? Q is equal to heat flux into the cross-sectional area. So this area, if you consider this area, this cross-section area, total, this is the normal to the heat flow direction, this cross-section area. That is the AX. So Q is equal to minus K AX dt. K dt dx. Okay. Now your consideration, where the physics is coming here. You see, T is a function of T is a function of X. So dt dx will be also a function of X. It will not be a function of Y and Z. So dt dx, there is no variation along X or Y direction. Dt dx, there is no variation along X and Y direction. But X we have fixed. So whatever the dt dx is at here, the same dt dx is at here, same dt dx is at here, and same dt dx is at here. Everywhere the dt dx is the same. Okay. Even over the plane here also the same dt dx. Same plane we are talking. So dt dx is the same over all X, Y, and Z points. Because X we have fixed in that condition. Okay. The area AX is also a constant. QX is also a constant everywhere. At same X, the QX is also constant. Because dt dx is a constant. Dt dx is the same in all, in a particular X. At a particular X direction, X distance, dt dx is the same, so QX is also same. QX throughout here, what is the QX value? Same QX, same QX, same QX. Everywhere is the same QX over the same distance, over the cross section. And we are considering here plane 1. As the plane 1, cross section area is constant. AX is also a constant. AX is also constant. So this is nothing but a constant. Total it is becomes as a constant. So heat flow is constant at X. Heat flow rate of heat flow is constant. It can be proved in mathematical levels, but conceptually I'm telling it in this way. What I'm telling you again, repeating, if you consider here, you can see K is a constant. Two assumptions because of it. One is the isotropic material. And another is the K very lesser variation with the temperature. Very less variation with the temperature. So K is a constant. GTDX is also constant at particular X distance. So QX is a constant. As it becomes a plane wall, AX is also constant. So entire Q is a constant. As entire Q is a constant, we can say that the Q, the variation of the Q with respect to X is equal to 0. The variation of Q with respect to X is equal to 0. That is a constant. Mathematically, we also prove it. That is the implication I'm going to give you, how mathematically we can say. In that case, you have to take one element. At this X distance, one small element in this way. One small element you have to take in this. One small element. How it will be looks like, we'll see it in the SSC. We just rub this part. So from the plane wall, if you take one small elemental area, at distance X, my drawing is not coming properly. In that case, if you take one small elemental area, it's quite better. In this element, the length of the element, if you take it as a delta X. Delta X. So it's a three-dimensional, it's a this side X, Y, everything is there. Three-dimensional case, we are not considering it here. Whatever. So over this element, there is some heat is coming in. That is, you take QX. QX is coming in. And what is going out? QX plus TX. That is going out. QX is coming in, QX going out. What are the assumption? Again, we recap. Isotropic material. The variation of K with respect to temperature is very small, so K is a constant, hence that is the first assumption. Second assumption, very important assumption, no heat generation or no heat removal from the system. From elemental system. No heat generation, no heat removal from the system. There is no heat generation is going on. There is no heat removal also going on. So, in such a cases, if you understand this thing, every calculation you will understand better. This concept you try to understand properly. Heat is coming here, heat is going out. In between, there is no heat generation or no heat is going out in different direction. In different direction. Other than this direction, other than the X direction, no other direction is happening. So whatever the heat is coming in, the same heat is going out. So we can say QX, energy balance, if you do, whatever the heat is coming in, the same heat is going out. Okay, that's the thing. What is the QX? QX is minus K X GTDX. What is this? This is Taylor series expansion we have to do because the coordinate is changing. That's why. GDX plus GDX of minus KX TTDX into del X, Taylor series expansion plus higher order terms also will be there. In such case, if you this elemental area, if you converge into a point, then differential expression will comes into the picture. Here, what you see, this will be cancelled out. And this will be cancelled out, and higher order terms you will see. So higher order terms, how it will come? It will come in del x square by 2 pi del x cube by in this. So in that case, what will be remaining if you take the limit del x tends to 0? You convert this element into a point. In such a cases, you will get it a very important equation d dx of minus kx dt dx is equal to 0. That means kx dt dx is a constant. Is a constant. What it is telling? What is the physical reflection in that case? K is already constant. We have assumed this thing. So from here we are getting it. Ax dt dx is equal to constant. For the plane wall, our consideration was the plane wall. Plane wall, the cross-section area is a constant. It's a plane wall. So whatever the area, this area and opposite area are the same. No changes. So individually everything is constant. Individually K is constant by assumption. Plane wall Ax is constant, so dt dx is also constant. So T, temperature variation, is a linear variation. Constant if you take C, so if you integrate, it will come Cx plus C2. So temperature variation, whatever you are getting, the temperature variation is the linear temperature variation. You will get the linear temperature variation. What does it mean? I'm rewriting this thing. If it is the plane wall, we concentrate on this thing is very important. The plane wall. If here temperature T1, if here temperature is T2, the along x direction. So this is the one linearly it is varying is linear. Linear variation of temperature. Gradient is the constant. dt dx is constant. For plane wall, where Ax is constant. Plane wall where Ax is constant. If Ax is not a constant, if Ax is not constant, that means cross-sectional area is not constant, in that case, Ax dt dx is constant. It is obvious. Ax dt dx is constant if there is no heat added or removed from the system. If there is no heat added or removed from the system, this is constant always. But if A is varying, AX, if it is varying, dt dx also will be varying. But multiplication of these two will be constant. Multiplication of will be constant. What does it mean? This is the concept. Exam question is coming from there. There the question will come to. If AX is increasing, cross-section area, if it is increasing, that means converging in this way. If it is like this way. If it is like this. Cross-section area along x-axis, is the x-axis direction is this side, x-axis. Along x, the area is increasing. In that case, the dt dx is decreasing. Slope, temperature gradient slope is decreasing. dt dx is decreasing. In that case, how the slope will be? In that case, how the slope will be? If you draw this thing, t versus x, if you draw here, t versus x, so it is x is equal to 0, this x is equal to L if you take. So at L, x is equal to L, it is x is equal to 0. That you take here, temperature was T1 is higher temperature T1. Here temperature is T2, lower temperature T2. How the graph will be? You see here, the temperature gradient is decreasing. As the temperature gradient is decreasing, it will be like in this way. Slope is decreasing. Decreasing slope. Each and every point, if you take the slope, initially slope is higher, later the slope is decreasing. That is the concept. Question is coming from this sense. Similarly, similar example. If AX is increasing, if AX is decreasing, in that case, the temperature gradient will be increasing. In that case, what will be happen? In that case, the slope will be increasing. And if AX is constant, so dt dx also. So it will be simply, if we join these two lines, this is the concept is coming. I'm making it fairly, it will gives you a better idea. X that you take here, that at x is equal to 0, the temperature is T1, x is equal to L, temperature is. If there, the area is 3, one thing is that if area is a constant, that means for the plane area cases, if area is a constant, it will come. Here. So it is the, if area is the, this is the constant area. AX is constant, so linear. It's a far more linear. If it is like this, slope is decreasing trend. Slope is decreasing trend. In that case, Slope is decreasing trend, area is varying. That is AX is here decreasing. Here AX is constant. Here AX is increasing. They might have given you the graph. Accordingly, you have to tell in what case what is happening. So that is the prelude of this part. So two-dimensional cases also we can tell in such a way. Two-dimensional cases. In the two-dimensional cases, the same if you take one trapezium here. Varying cross section. It is varying. Cross section along the X, cross section is varying. The X direction, cross section is varying. In that case, you have to see the temperature variation along X and temperature variation along Y, both are existing. Both are existing. So it becomes a two-dimensional steady state problem. It is not a temperature, is not a, there is no existence of the DT. There is no existence. There is a two-dimensional conductive heat transfer problem. It will like. So here the basic prelude of conduction heat transfer is here. Next will come one by one a mathematical model. Taking one plane wall model, we'll discuss definitely what kind of the boundary condition will be there and what is the actual conduction equation. We have to solve it. Heat conduction equation. One by one will come. Later is some idea about the convection phenomenon and radiation phenomenon also we'll discuss, and then we will complete this first basic chapter. Then we proceed to the convection one by one. Thank you.